Good evening and welcome. I'm Jennifer Walsh, Dean of the College of Environmental Design. Thank you, everyone, for joining us this evening for what will without doubt be a compelling lecture, exciting lecture by Janine Benyus, founder and president of the Biomimicry Institute, who was recently named by Business Week as one of the 30 most influential designers in the world. So we're really pleased to have her with us this evening. Tonight's lecture, as well as last night's lecture by Professor Paul Collier, and tomorrow evening's lecture by Barbara Maria Stafford, and Saturday morning's lecture by Manuel Castells, and also I'm sure what will be a masterful sum up of our activities over the last few days, Dana Cuff from UCLA. All of these activities have been organized as part of the College of Environmental Design's 50th anniversary celebration. Last fall, we had a series of celebratory events to pay tribute to the college's history and legacy, featuring reflections from distinguished alumni and emeriti faculty and major lectures. And there was a lot to celebrate. In 1959, the College of Environmental Design was established as the first school in the country to combine disciplines of architecture, planning, and landscape architecture into a single college. And CED paved the way and really led the way toward an integrated approach to analyzing, understanding, and designing the built environment. CED was also among the first to conceptualize environmental design as inseparable from its social, political, economic, and cultural contexts, and to stress the importance of bringing science and scientists into planning and design areas. At the same time, the college has historically emphasized environmental design as a profoundly ethical practice, co-produced through dynamic engagements with communities, workers, businesses, and policymakers. Linking theory to practice, the college's faculty and students have long been known for what we call design activism, building housing for homeless people, creating new models of affordable housing, uncovering patterns of environmental injustice, and collaborating with communities to design parks and open space. The question that we have before us as we turn 50, actually I have to admit I turned 50 a while ago, but be that as it may, the question that we now have to ask is, what's next? We've turned 50, what does the next 50 years look like? What should it look like? What's our future? The college was prescient and ahead of its time in 1959. And I think we need to remain as forward-looking and inventive today, even if the future that we face is far different, radically different indeed, than what we thought it might be in 1959. We have to dare to raise the urban question and struggle for social justice in the city, make buildings that are at once elegant yet sustainable and regionally appropriate, push the frontiers of high-performance design and rigorous building science, join with grassroots groups in the making of well-loved places, and above all, perhaps, envision human settlements of the future, replete with social meaning, ecological value, and possibilities for health and livelihood. This is a tall order, and it raises critical questions, such as, what should we be teaching aspiring architects, planners, urban designers, and landscape architects, people who will be doing the planning, designing, and building of the future's human settlements, all the way from the scale of the individual home and garden to global city regions? What skills do they need as the 21st century unfolds? How will the context confronting environmental designers shape the demands for future research and practice? This semester, the spring semester, as the second part of our 50th celebration, we begin to grapple with some of these challenging questions. We do so through an exploration of some of the most profound problems facing the planet, such as global poverty, which was the focus of Professor Collier's lecture last night. And we hope to glimpse some of the most intriguing ways to rethink environmental design. We're certainly going to hear about some of these approaches this evening when we hear Janine's lecture on biomimicry. and as she explains to us how we might harness models from the natural world to reshape our materials and the metabolism of cities to protect our ecosystems and our climate. We will also explore tomorrow night with Barbara Stafford models of cognitive science and neurobiology to understand human attention, visual perception of the world, and ultimately creativity, which lies at the core of environmental design. And on Saturday, Manuel Castells will focus our attention on how grassroots movements around the world are emerging to reshape the city, its politics, and its space. Also on Saturday, we'll listen to the voices of our younger generations, recent alumni, assistant professors, graduate students, as they debate the future of our college and community, the problematics that ought to drive our theoretical exploration, and also the modes of practice that might be capable of tackling the challenges that lie ahead. So I hope that you have marked on your calendar another evening tomorrow night and a Saturday morning at Worcester Hall that should be fascinating and very provocative. I'd like to now introduce Professor Gail Brager, who will in turn introduce our esteemed guest speaker. Professor Brager is a professor of architecture, and she's also interim chair of the Department of Architecture. She's a mechanical engineer by training and a building scientist by practice. She's also affiliated with the Energy and Resources Group here at UC Berkeley, and she's also an ASHRAE Fellow and past president of the Golden Gate ASHRAE chapter. For those of you who don't know, ASHRAE stands for American Society of Heating, Refrigerating, and Air Conditioning Engineers, which seems like an arcane technical organization, but in fact is hugely influential in setting the codes and standards that shape building performance, and hence the contribution of buildings to greenhouse gas emissions and climate change. Professor Brager has published extensively on topics including thermal comfort, adaptation in naturally ventilated and air-conditioned buildings, task conditioning, and indoor air quality. She received the coveted NSF Presidential Young Investigators Award, as well as many other significant awards, including a Progressive Architecture Research Award and awards from the AIA. Gail teaches in the areas of energy and environmental management, sustainable design for hot climates, mechanical systems and architectural space making, and research methods. And she's currently conducting research on naturally ventilated building performance and occupant comfort and the design and performance of alternative office spaces. So I want to introduce now Gail Brager.
Thank you, Jennifer. Well, a long time ago, and in a place far, far away, there lived a simple nature writer by the name of Janine Benyus. Formerly trained in biology, natural resource management, and English literature, Janine was, by her own account, I believe, a nature nerd. She loved nothing more than to wander through the forests, the canyons, and the rivers, observing animal behavior, and then running home to pore through all the scientific journals she could get her hands on to better understand the variety of organisms that inhabit our planet Earth and the exquisite ways that they adapt to their places and to each other. Well, as time passed in our story, over the course of 10 years between 1983 and 1993, Janine wrote 5 books about wildlife and animal behavior, ranging from field guides to the secret language and remarkable behavior of animals, to beastly behaviors, a zoo lover's companion. But as she learned more and more about how well animals create, manage, and adapt to their environments, a funny thing happened. She became more and more bothered by her observations about how poorly human beings do the same thing. And that angst that she felt turned out to be a very good thing for all of us, because she turned that combination of frustration and curiosity into a new direction of research, which resulted in the book that many of you know called Biomimicry, Innovation Inspired by Nature. And starting with this book and in the spirit of activism that we try to strive to teach our students, she essentially created a new movement that changed the way many people think about design. You know her as the founder and president of the nonprofit group, the Biomimicry Institute, but I want to make sure that you know about an amazing website that they recently launched that I encourage you to check out called asknature.org. And it's basically a public interactive database of biological literature that's organized by design function, and something you're free to explore and also add to. So, what is this strange term, biomimicry? We're going to hear a lot about it tonight, but beyond Janine's own explanations, one of my favorite comes from Avery Lovins, who said that biomimicry is wise adults in a rainforest with flashlights. It is luminous humility, where we treat nature as model and mentor, cherished not as a mind to be stripped of its resources, but as a teacher. Now, for all of you who have been asked to introduce somebody, what do? We think, how can we describe them in ways that will make them bigger than life? And in many ways, Janine has indeed been characterized as one of the big thinkers of the sustainability movement. But I like to think about Janine in a different way. I think that Janine is a small thinker. She starts with understanding the biological functions of the smallest details within nature. Maybe it's the stickiness of the bristles on a gecko's feet, or the durability of spider silk, or the spiral structure of a nautilus shell, or the flexibility and resilience of the abalone. I think she asks small questions, like how little damage can we do to the environment? And how much less can this cost? A small thinker she is. But please don't underestimate the result of such small thinking, because her impact has indeed been enormous. As Jennifer mentioned, just this week, Business Week published a list of 27 of the world's most influential designers, and Janine was deservedly among them. She's been honored by Time International as one of the heroes of the environment. She's received numerous awards, including the Rachel Carson Environmental Ethics Award and a Champion of the Earth Award from the United Nations, and many others. But instead of going on and on and on about her list of accomplishments, which I certainly could, I'd like to instead describe why I believe that the way in which Janine thinks, operates, and creates makes her a perfect person to be speaking to us tonight on the occasion of our 50th anniversary to address the theme of visualizing the future of environmental design. I believe that Janine embodies much of what we try to teach our students in the college. Since her groundbreaking book, Janine has immersed herself in the world of design. She is the biologist at the table and is an integral part of the creative process. She thinks outside the box, drawing on multiple disciplines, which is what we encourage our students in environmental design to do. I see her as the center of a spider web, if I may borrow a biological metaphor, which we've been doing all day, weaving together the disciplines of biology, ecology, architecture and engineering, planning, material science, business, and many others. In fact, this morning we had a delightful time meeting with many faculty from various departments around the campus, and I'm pleased to report that we are starting a process of developing a new minor at UC Berkeley in biomimicry. So stay tuned, and we will inform people about that. So thank you, Janine. She is our inspiration. So Janine works at different scales, which you may see tonight, starting from materials and components to building envelopes to landscape and planning. And in that regard, we hope our students find inspiration in this and see themselves, regardless of the department they come from, as part of the larger college, and that they explore outside of their own department to think about design at these different scales as well. I like that Janine works beyond the metaphor. She pushes clients to explore the connections between design and real performance, and looking at both their social and environmental implications. These are also founding principles of our college. At the design table, she rejects simple questions that start by presuming a solution and simply asks, "Tell me how to do it." Instead, she pushes her clients to instead think about the function. What do you want this component, building, skin, or city plan to achieve? And then she gets to be the detective, sleuthing through various knowledge bases to find specific biological examples that designers can learn from. And this is exactly the kind of critical and original thinking that we hope our students will be inspired to do as well. But I would close by saying that I think one of the most important things that I think our students can learn from Janine is that she has fun doing what she does. And I think her brilliance and passion for her work will be evident tonight, and I'm confident that you will be as moved and inspired as I am every time I hear her speak. So please join me in giving a very warm welcome to Janine Benyus.
Good evening. To stand here, and I know that there are a lot of people in this audience that I know and that I love, and to stand here and to introduce you to characters like this. Oh, he'll come up here soon. Let's go back a few. Let's get to the good stuff. To introduce you to characters like that, that's Revenge of the Nerds. That I get to do this is Revenge of the Nerds. How many students here? All right. How many of you are proud nerds? Come on. It's going to be great. I am living proof that somebody who literally grew up watching grass grow and being excited about it gets to be here with all of you and spend an evening. Thank you for spending your evening with us. And happy birthday, 50 years. I cannot believe you guys were way ahead of the curve. And I can tell you from experience that it's a flipping point. 50's a flipping point. And you realize that you now know what you want to be when you grow up, and it's not a grown-up. And you do not care as much what other people think. And that means that most of what you do is in the outrageous category. So welcome to the next 50 outrageous years, College of Environmental Design. I have the pleasure of talking to you about things we might learn in the natural world, about the built world, about our world. Our largest artifact, humans' largest artifact. It's a big, big colony of nests we've created. And interestingly, in the next 30 years, 80% of the buildings in this country are either going to be remodeled or built new. So you guys are going to be building our largest nests. Hopefully these guys can help you. I'm noticing that buildings are getting curvy. They're really getting very, very curvy. And I have many theories about this, and probably you would cringe. They're not academic theories about it. But I think, I think we are yearning for something that reminds us of ourselves. Something that reminds us of that beautiful tree that we glimpse speeding by the window of our high-speed train. I think we yearn for that thing that softens the stone-like part of our heart. That thing that when we sink into the scene, it allows us to hear our own heart beating again. I think that the curvy architecture might be a yearning for a homecoming. But I think that the curviness is not enough. What I want to talk about tonight is the fact that biomimicry, looking to nature for inspiration, is not, the outcome of it is not just about curvy buildings. It's about function. It's about choosing the curves that you choose because they allow a building to withstand Katrina-sized winds, or choosing an angle on a building because it allows wind to wrap around so that you can catch it with a wind turbine on the other side, or choosing a shape that will allow floodwaters to come, part, and recede without damage. Choosing form because of what it does, not because of what it looks like. And biomimicry is very much about that. It's about not just how nature looks, but how nature works. And I think that what we're yearning for is that this performs like this. I think that's what we're hoping for. I think we better bet on it as a species. This is where I live. This is Stevensville, Montana. Those are the Bitterroot Mountains. This is, believe it or not, the view from my office window. And something very interesting happens every year. And it's something that I think would be an incredible design program for you to think about. Design this. Design spring. It's not just how it looks, it's how it works. Can you imagine designing what would need to happen for spring to arrive the way it does every single year? It is a bottom-up emergent phenomenon from organisms by the millions that have struggled with exactly the things that we've been struggling with, which is simply, how shall we live here in a way that creates conditions conducive to life? That's the center of the sustainability movement, and it is something that these organisms have been working on for a very, very long time. So when you're up all night looking for a good idea, walk outside. Sorry, this is a little, there we go. So biomimicry is learning from the locals. These are some of the locals that are around my part of the world. It's also a conscious emulation. It's an emulation of form and hopefully an emulation of process as well as form. Processes like photosynthesis, processes like natural selection. And it's also hopefully a mimicry of ecosystem level phenomenon. And I'm going to try to talk about all of those tonight. I'm going to try to touch on all of those. The other thing that I want to do tonight is to remind you that you're not just alone in terms of, you've got plenty of natural elders outside, but you are also in a university where there's a lot of biomimicry going on. And I've tucked some of the research projects that are going on here at Berkeley in this presentation. And so if you are a student working in the design disciplines, there are some biologists that you should meet. They're nature's apprentices. The field, let me give you a little idea of the field of biomimicry and how it's growing. It was a study done by Richard Bonser, and he looked at the years between 1985 and 2005. He looked at the worldwide patent database, and he looked for the words bio-inspired and biomimicry and biomimetic. These are all synonyms. And he found that the patents in this field have increased by a factor of 93 times. So it's really this ski slope of new patents coming out. Now that's against a background rate of 2.7 time increase in patents. So it really is, a golden age in this field. There are, in addition to a lot of patents coming out of academia and a lot of small companies starting up, there are also a lot of established Fortune 50 and Fortune 100 and Fortune 500 companies that in their R&D labs, in their engineering studios and their design studios, they're asking biologists to come in. Biologist at the design table. That's the career that I now have we call it BAT, B-A-D-T. These are some of the companies that we work with. Our company's called Biomimicry Guild, and we're a group of consulting nature nerds sitting at the table. We are asked by our clients lots of questions that have to do with function. Not what they want to design, but what they want their designs to do. These are the kinds of questions that we're asked. How does nature reduce friction? How does it seal leaks? How does nature store energy? Read new battery, which we need. And we do these things called amoeba through zebra reports, in which, get this, for a natural history writer, this is a career of a lifetime. I get to basically do a library safari through the biological literature, looking across taxa, looking at bacteria and fungi and plants and animals, and using a functional lens to pull up the strategies that life's evolved over 3.8 billion years, and present those to an inventor who most of the time has never thought of any of them. It's a wonderful career. Any biologists in the audience? A few, good. So one of the things that we find a lot of deep principles float to the surface as well. While we find principles around each of these functional terms, we also find some ubiquitous things that the natural world does over and over and across taxa. And one of them, I talk about the fact that it taps the power of limits. And what I mean by that is that in the rest of the natural world, limits are not a negative thing. They're not something to be overcome. They seem to actually be a creative frame. Organisms deal with the limits that they have, the limits of the kinds of nutrients they have available to them, or the kinds of temperatures that they've got to deal with, and they learn to dance within those limits. And the ones that really excel are those that have learned to elegantly respond to those limits. The elegance that we see in the natural world, we assume that it's visual elegance. But I think on a deeper level, after spending 200,000 years in the presence of some of these organisms, I think we recognize good design when we see it. I think we love these scenes because on some level we recognize that they're healthy and that they work well. When I look at this scene now, after working in biomimicry, I see it as a solar array inspiration site. I mean, every single one of those organisms are, yes, they're all fighting for sunlight, right? They've got this limit, right? But look at all the different strategies. Look at all the ways that they're finding that sunlight. That's the creative frame. And I'm hoping that in this carbon-constrained, peak oil, peak soil, peak water, peak mineral society that we're moving into, that you're going to design into, that you'll see these limits as a creative frame. Now, at the risk of having this lecture be known and having me be known forevermore in your minds as the slime mold lady, I am going to introduce you to one of the most incredible organisms that you will ever encounter. I mean, it's got slime in its name, and it's got mold in its name. It is a slime mold. It is not a fungus. It is in the Protista kingdom. And if you look very carefully, and in this part of the world, go to a moist redwood forest, look at the logs on the floor, chances are you'll find some of these guys. They will be blobby, jello-like looking things that might look like that. They're orange and pink. They're really spectacular. But they're a very interesting organism. This is not a single organism in the way we think of it. This organism starts its life as amoeba-like individuals that are spread around the forest. And when there's a realization that there's a good food source, like a good log, they eat bacteria and spores. And if there's a good log that has a lot of bacteria growing on it, they will begin to signal to one another. And they do this thing called quorum signaling. And they will all start to gather towards that log. When they get to the log, they aggregate and become what looks to us like a blob of jelly or one organism, okay? And they start to do this thing called protoplasmic streaming. They're really incredible. And then at some point, when the food source is not as good anymore, they decide, no one knows how, among themselves, to create a stalk and to create a spore capsule on top of that stalk. And that spore capsule eventually breaks open, and the small seeds of the next amoeba-like organisms go spreading out again. That's its life cycle. You really have to start looking for these guys. That's the stalk and sporangium side of it. They're not ferns and they're not fungus. Very interesting. There's another. These are all different. Aren't they beautiful? See? I know. I know. I love these guys, and now you do too. Wait till I tell you what we're learning from them. I mean, really, it is the small thinking thing. One time, I gave a talk, and these guys came up to me and they said, "Could you wait here?" And they were First Nations people. This was in Canada. "We want to bring our elder back, our chief of our tribe back." And I said, "Sure, sure." And I just stood there in the hallway, and he came back, and I said to him, ridiculously, I said to him, "Yes, we're looking at the best and brightest in our habitat and see what we can learn from them." And he just put up his hand and he said, "No." And I said, "No, okay." And he said, "It's the smallest that you'll learn from. It's the maligned, it's the slime mold." And it's true, it's true. Look at these. Talk about, just a lesson in community development as well. Look at this. This is incredible. Who decides who gets to be part of the sporangium and who's the stalk? Right? Streaming look. I mean, really. These are amazing. This one's called a chocolate slime mold. And being at the university, I cannot pass the opportunity to tell you about the vomit, literally, the vomit slime mold. I'm sorry, but it actually grew up that beer can, that yin-yang beer can. But this is what I want you to look at. Now, when they do this protoplasm streaming, what they do is those networks are where they pass the nutrients around. So say over here there's a nice nutrient node and a nice nutrient node, there's something to eat here and there's something to eat here, and they pass the nutrients through these. But what happens is they start out just as like a wash of a wave. They literally start out as a fan, and then in the areas where they don't have nutrients, they contract. And they concentrate, basically, where the best nutrient flow goes. Okay, the nutrient, and it turns out, and scientists are curious and thought, is this an optimum way to distribute flow? Well, there's a Japanese and an English. These are two different universities, and they did two different sets of studies. Believe it or not, this is a picture of Japan and the cities around Japan, around Tokyo. Here's Tokyo, and they put oat flakes, I guess are yummy to the slime mold, in the cities around Tokyo. The protoplasmic streaming began, and it went out, and then it began to optimize. And it took away from where it didn't need to have the nutrient tunnel, and it put the nutrient tunnel where it needed to be, and it drew, after 26 hours, the subway system around Tokyo. The same subway system. Very, very, almost eerily similar. Same thing happened. This is England. Same thing happened here. This is the roadway system of England. Very, very similar. Now, what happens in biomimicry, you say, well, now are slime molds going to replace traffic engineers? Maybe. But fear not, traffic engineers, because mathematicians got involved in this and basically looked at what the important thing here is that there's an algorithm. There's a mathematical representation of this. Because basically this is an optimizing program. You know, it says only put things where they need to be. And where nutrients are coming, and we see nutrients coming, let's reinforce that, and let's take away what's not needed. Life taps the power of limits, and like Picasso, makes art out of taking things away. It's very different than what we do when we, for instance, put as much material as we can in a building to bolster it just in case. It's a very, very different paradigm. So, learning from slime molds is fascinating. But a bigger question for you as students is what's worth doing with that knowledge, right? What's worth doing, or what's worth solving? And what I would say to you is please do not make widgets. Don't make chia pets. You know, with your design knowledge, solve the worthy challenges that we have, and we have plenty of them. Here's a design program. This is Adam Neiman's work, and this is a depiction of all the fresh water, all the salt water, all the ice, if it melted, okay? All water on Earth, the volume of all water on Earth, not just fresh water again, all the water on Earth, in relation to the volume of the Earth. And this is all the atmosphere that we can live in relation to the volume of the Earth. And what happened over long, long periods of evolutionary time is that the organisms that emerged from this planet, this ball of rock and sea, made a lush and livable place. Sweetened those waters, sweetened that air, literally created the cocktail of gases that we breathe today, helped to create that. In other words, living beings help and continue to help freshen that water and freshen that air. And what we need to do, we're inside there. And what's worth doing is for us to learn how to do it too, I think. So, I'm going to go through some of the questions that you probably get asked as architects, planners, landscape architects, product designers. And you'll see and hear the word without, because I'm really trying to reimagine limits. And without is not a dirty word. Again, a creative frame, a way to elegance. So how do we get energy without fossil fuels? This is where I get most of my ideas. Hopefully, you are still close enough to this. Has anyone done this lately? Okay, you have to do this. You really do have to do this. This is the major energy system on our planet, photosynthesis. Current sunlight, we go to ancient sunlight in fossil fuels. It's sunlight that was captured millions and millions of years ago. This is current sunlight. And this is really where we need to go. There are a lot of people, including people at Berkeley, that are learning from photosynthetic organisms, leaves and blue-green bacteria, cyanobacteria. And they're learning many things, including having sunlight to electricity. But really, that's not what these plants do. What plants do is they take sunlight and they turn it into chemical fuel. They turn it into sugars and starches and ATP. They turn it into stuff. Not really electricity. So that's what people who are, these are people you can go and visit. This is the Graham Fleming lab. These are leaf peepers. I guess they're wearing their lab stuff. The Graham Fleming lab is working on grabbing photons, yes, and turning those photons into electricity, but also into other fuels, as you'll see. This is Grant Fleming, and one of the things that the lab has found out recently is that they think that plants are, that the antenna that pulls down sunlight, that pulls down those photons, there's a drizzle of photons, and 2 photons have to land within impossible sort of distance of one another, time-wise of one another, in order for that whole photosynthesis magic to work. The chances of that happening are really outrageously slim, and yet it does every day, over and over. And part of what it might be, they now think, is that the antenna function of the leaf is working with quantum mechanics, that it's actually quantumly entangled, that it actually tries out all energy paths simultaneously and chooses the one that is most effective, kind of like the slime mold. Quantum beating, they call it. And that's what they have discovered. A lot of biomimicry begins with this fundamental research. Oops. Now, the people who I talked about in the book, the people who are studying leaves to come up with new kinds of solar cells, that the actual product that you can buy today is called dye-sensitized solar cells. They are based on leaves, dye-sensitized, they're based on pigments. So they're very different than how silicon PV works, or even how other thin films like cadmium telluride or SIGs. Very, very different basic mechanism. The mechanism that's based on a leaf is a dye-based mechanism. And there are companies, as you look in the right, you'll either see universities that are working on things or actual companies that are actually selling things. Now again, the big thing is that a leaf does is it takes that sunlight, moves it through that antenna, and then it uses that energy to split water. The oxygen comes to you, you give carbon dioxide back to the plant, the oxygen comes to you, but then there's also a hydrogen proton that comes out. Now if you put 2 of those together, you get hydrogen gas, which you can put into a fuel cell. It's an energy carrier, and you can put it into a fuel cell. So a lot of people are looking at figuring out a catalyst that works like the catalyst in the leaf, that we would be able to take a solar cell and then have it attached to a catalyst that would then split water and bubble off hydrogen for us. But there's something else that you can do, and a lot of people are working on this. As you can see, there's a ... because lots of people are working on the water splitting. But then it's, what can you do with this electricity? Organisms actually make it into something. What if we made it into fuel? What the plant does then, after it splits the water, is it takes the carbon dioxide in the air and turns it into sugars and starches. So what if we turned that carbon dioxide, if we took that C, and we turned that into, say, some sort of a liquid fuel? A lot of people are working on this as well, including a guy right here, Paul Alavestos. I'm not sure exactly how to pronounce his name, but he's at Lawrence Livermore, right here. Again, here's another without. I live in a hard rock mining state, Montana, and I have watched 50 years of mining tailings still acidifying and poisoning streams. I live in the most pristine state in the world. I live near the biggest Superfund sites in the world because of hard rock mining. So is there a way to get what we need that's already been dug up? What happens with us is that we go in and we mine something that's concentrated, and then we make it disparate. We spread it around, and then it's very, very difficult to get it back again. What life does very well is concentrate things that are spread to the winds. That's what life does very, very well, including minute amounts of metal, for instance. So the question is, can we be more like the organisms that are able to get locally abundant materials and pull them together and make them into, for instance, the building materials that they need? Here's an example, and this is from a new company called Calera that's right down the road from you folks, that has Moss Landing, the Moss Landing utility plant. They are doing a demonstration project here. And Vinod Khosla, who's a VC, a clean tech VC, has invested in them. What Calera does is it uses the recipe from the coral reef to take CO2 out of smokestacks, combine it with seawater, and make the raw materials for concrete, for cement, okay? Concrete is 6 to 8% of all CO2 emissions comes from the making of this it's the building material that's most used around the world is concrete. The cement part of it is where most of the CO2 emissions, that's the glue that holds everything together. Calera, this is a scientist who was a coral reef expert, expert on how bones form, and an expert on how your teeth form, biomineralization expert. He took this recipe, and he is now taking a waste product, which you and I think of a waste product, CO2, and embedding it in concrete. Instead of, used to be that a ton, or still is for most concrete, a ton of CO2 is emitted for every ton of concrete that's made. And he's reversed that, and now he's sequestering a half a ton of CO2 for every ton of concrete. Those are the kinds of mimicries, the mimicking of the coral reef, the mimicking of seashells that I think we need to be doing. This is where we now get the raw material for our concrete. We go to a limestone cliff, which are the bodies of ancient sea organisms, and we dig them up, we grind them, we mine them, and then we make them into cement. Instead, why not take the CO2 that's right here as the raw material and seawater and make concrete where you need it, which is right at the building site. Interesting. Real, and there's another company called Carbon Science. Now, Carbon Science is looking at taking CO2, a carbon neutral idea, taking CO2, and they're mimicking bacteria that are able to take CO2 and actually make hydrocarbons out of them, like methanol. Now, that's a carbon neutral idea. So what's interesting to me about this is that right now, like, compare it to biomass to fuel. You've got biomass, you know, whether it's corn or whether it's switchgrass, you're still growing it, you're harvesting it, you're transporting it, you're producing it at the biorefinery. There's a biofuel distribution infrastructure. They're looking at using a biocatalytic process and taking CO2 and going directly to a fuel, to a liquid fuel. Here's a guy who is taking CO2. This is a company called Novomer. They're taking CO2 and making biodegradable plastics. Again, a CO2 as a feedstock for a raw material that we need. Another carbon neutral idea. Life also tends to use multifunctionality. That's another big one. It's an optimization rather than a maximization. So if you look at something like this, if you look at this chip bag, it's got about 7 layers in it. So you got a layer for waterproofing, you got a layer for ink, you've got a layer for breathability. Every time you have a new function, you add a new layer. Here's an organism whose exoskeleton is waterproof, is breathable, is resilient and yet tough, resists abrasion, is creating color through structure, all in one material. It's another really deep pattern that we see is that in the natural world, the material is the system. So material scientists are really important to this revolution as well. Polymers, plastics. In the natural world, you have about 5 kinds of polymers that make everything. And this is really helpful because when it comes to recycling, you've got simple building blocks that build through structure and design into complexity. But the building blocks themselves are repetitious and simple. We have about 350 different kinds of polymers. Because every time we want a new function, we make a new polymer. So again, another design program for you guys. Make the world out of 5 instead. add design to get the function that you want. Water without wells. What if we were to close the straws that we have in aquifers right now? I'm working right now with a group in China. There's actually people here from a Chinese delegation. And we're looking at how can we stop dropping the water table below the North China Plain. It's dropping 1.5 meters every year right now through agriculture. Water, peak water, is the new peak oil. So how do organisms get water without digging wells? What are they doing? Well, they get water in places, remember I talked about concentrating disparate things. Fog is very, very difficult to capture, it turns out. It's in very, very small droplets. This beetle has figured out how to do it. It has these bumps on its back. This is a beetle from the desert, the Namibian beetle. And fog comes in. A couple of times a week, fog comes in. At 50 miles an hour, there's a fog wind coming in. But it's very hard to grab that. But it's found a way. It's got bumps on its wings. And at the tips of the bumps, there's hydrophilic part. And at the sides of the bumps, there's hydrophobic, water shedding. And what happens is that a fog molecule, a droplet, will start on that tip, and then more will join it, and it'll begin to grow until gravity takes over, and then it goes down the waxy shoots and into the critter's mouth. I mean, it's a beautiful, elegant thing, and people have mimicked it. A company called Kinetic. What they've done is they've just basically taken checkerboard squares of hydrophobic and hydrophilic squares next to each other. And what happens is that water comes in, it builds up, and then it moves away quickly. When this critter is on the sand dune, within a few seconds there's a stream of water into its mouth. And that means its back is available for more fog capture. Now, can you imagine buildings doing the same thing? Here's a concept sketch of a building in the Canary Islands off the coast of Spain, architecture firm called Grimshaw. Can you imagine watching a theater performance, knowing that on the other side of that, the fog is being captured for irrigating the landscape? Imagine at the tops of the buildings here in San Francisco when the fog comes in, that in the morning your building captures fog, captures water to flush the toilets in the building, not needing to pump them up. This air-to-water technology is really cool, and I saw a student in the environmental design college working on something very similar to this today. Life is really, really good at recovering fresh water from salty water or from water that has solutes in it. And I say it that way for a reason. What we tend to do is we push water in reverse osmosis, say for desalination. We push water against a membrane to sieve out the salt. And then, of course, the pores clog. And so we add more pressure, 900 pounds per square inch of pressure. And we keep pushing, and we keep pushing, and like Lord Dyson says, it stops, it clogs. What life does, these are little pores that are in every one of your red blood cells, for instance. They're very, very common. They're called aquaporins. The chemists won the Nobel Peace Prize recently in chemistry for discovering them. They are an hourglass-shaped pore that escorts water molecules through, pulls water molecules through, leaving everything else behind. Forward osmosis, if you will. Pulling water through rather than pushing against. What an elegant thing. There's a company called Aquaporin. They're not just doing desalination membranes, they're also looking at salinity power, because using osmosis as a way of getting small amounts of energy along this, and together, actually, a lot of energy along these membranes. Flow without friction. That's a Mercedes-Benz concept car. Gets 70 miles per gallon. It's based on this character, this boxfish, a coral reef fish that really doesn't go very far. It actually is hydrodynamic. It sits in the coral reef. The water goes around it. Turns out that shape when they modeled it and they put it into water tunnel tests, it had almost a perfect coefficient of drag. The most perfect shape engineers believe is a teardrop shape, basically. And this was as close as anything had gotten to that coefficient of drag. Plus, it sits 4 comfortably. Here's a cool picture. So a Czech photographer sent this to us. This is a kingfisher, and what do you notice about the water by his beak? What? No ripples. No ripples. Really amazing. Why? Function. The eyes have to see the fish, right? So J.R. West is the manufacturer of the bullet train in Japan. The bullet train was called the bullet train because it had a rounded front, which as it went through tunnels in Japan built up a pressure wave ahead of it. And as it exited the tunnels, it would create like a sonic boom. So this engineer, his boss said, would you quiet the train? And that night he went to the equivalent of an Audubon Society meeting. And he saw a film about these guys, these kingfishers, that go from one density of medium, the air, into another density of medium, the water, without splashing at the point of their beak there. Now, if you go to Japan, that's what the bullet train now looks like. And it happens to go 10% faster. It is quieter. Happens to go 10% faster, uses 15% less electricity. So this elegance, sometimes it scales. This is a company called Whale Power, and they looked at the scalloped edges on the leading side of the humpback whale flipper. This is actually work that was done by a guy named Frank Fish. I told somebody about my nominative determinism. I collect these. Well, Frank, his middle initial is E, so it's Frankie Fish. And this is a mammal, and I don't know. But anyway, the work was done, and then they actually started a company called Whale Power, and those are called tubercles that are on the humpback whale. And what it does is it actually enables that animal to be incredibly graceful. You know the ballet that they do during bubble feeding, right? They're able to turn in very, very small diameter spirals to do their bubble feeding. They're very hydrodynamic, and a large part of it is because of these tubercles. That effect has been demoed on wind turbines. The idea is that it not only reduces drag by 32%, but it increases lift by 6%, which means that wind turbines can rotate at lower wind speeds. The other thing that they've created that is now being sold actually is a large, large fan. It's a competitor. I guess there's a fan company called Big Ass Fans. You heard about this? That are in like, big, industrial buildings. And they're a direct competitor of Big Ass Fans, and they're whale power fans instead. Here's a good character here. Now this toucan, I gotta get a better picture because his schnoz is really big. That beak is really large compared to the size of the bird. And it's great for getting into fruits and nuts the way it needs to. But it's got an amazing material to strength ratio. It's very, very lightweight, and it's been studied, and it's got this wonderful sort of rigid shell around it. And inside it's this tiled, porous sponge structure that excites material scientists. And so people are trying to mimic that. That's going on at MIT in Lorna Gibson's lab. But life does this very, very, very well. This, the boxfish car, they had so much fun with the outside shape of it, they decided to try to make it bio-inspired on all levels. And so one of the things that they worked on was the skeletal frame, and I use that word because it does kind of look like a skeleton, doesn't it? But it is not the skeleton of the boxfish. It's very similar, and you'll see what I mean, it's kind of similar to the slime mold example, in that it is based on an algorithm that what comes from bones in trees. When trees get knocked down by the wind, they respond to go back up to the sun. And there's a guy named Klaus Mathek who studied this for 30 years, and he tried to figure out, is there a design principle behind this sort of reaction to stress? And indeed, what he found in the tree was that trees try to equalize stress along all their surfaces. And so in their reaction, as they react, they equalize stress along the surfaces. That went into one software program. Then he looked at bones, and he looked at how our bones, as we walk through our lives, they're always responding to stress, and they're taking material away from where it's not needed, like the slime mold, and putting it where it is needed. Okay, so beefing it up along lines of stress. He put that into a software program. When they ran that software program, and they said, this is the stress that this car is going to be under, these optimization programs, these software programs, came up with that. So that's a minimized, it's a light-weighted frame, using the minimum amount of material to get the function that you want. And those two software programs are available, being used more in Europe. But imagine using that, for instance, in structural members in a building. Imagine the sustainability benefit of something that would put material where you need it and take it away from where you don't. This is an organism that's made of glass. This is Joanna Eisenberg's hand. She's a real hero in the biomimicry academic world, material scientist. These are sea sponges. This is the skeleton of a sea sponge that's called Venus sea basket. She studied two things. She studied the filaments that are fiber optic-like. They are actually waveguides. She and her team studied the structure that you see here. You see it, and this is, again, it's made of glass. Very delicate, very strong. Don't be surprised. I mean, this is a delicate material that has been made strong through design. And it's on many, many levels of hierarchy, it's strong. Her team did a study, and they found 7 construction methods that we currently use that are in this particular structure. Really, really interesting. I can share that with you. And when you look at things like the Swiss Re building in London, and you look at all that lattice structure and those diagonal, almost fibers that go around, it's very similar to what's going on here. But the construction methods that we've come up with, this organism, millions of years old, has been using for a very long time. This is Don Ingber, who's also at the Weiss Center for Biologically Inspired Engineering at Harvard. And his study was of tensegrity, which is a term that you might know from Buckminster Fuller. You might know if you love sculpture. This is Kenneth Snelson's tower that is a tensegrity tower. And what it is that it's struts and cables. You sometimes see it in those toys that you get that you can compact and then the ball pops back out again. It's a way of distributing forces through something that's cable-like and something that's stiff. Very much what you have in your bones and your muscles and your tendons. Your bones are the stiff part, your tendons are the more rubbery part, the more flexible part. Well, Don went all the way down to the level of a cell, and this is a depiction of the cytoskeleton. There's skeletons inside your cells that make your cells not watery sacs, but actually give them structure. And lo and behold, tensegrity. So some of the most beautiful things, if you're in the design profession, biology has a beauty. And that beauty has to do with things like this, where tensegrity is at the largest level of your bone and skeletal structure. It's also at the level of inside your cells. And architects are beginning to use tensegrity as well to lightweight things. Now here's something that, what what we want in our buildings is a responsiveness, an adaptiveness. That's where more and more people are talking. When they talk about living buildings, they talk about buildings that are aware of what season it is, of how high the sun is, of whether the wind's blowing or not, and whether they should close the awnings or open the windows. And the Holy Grail really is to say, you know, wouldn't it be great if the buildings responded like a leaf responds? You know, when a leaf is constantly opening up its pores and closing its pores to let carbon dioxide out or to let oxygen in. And it chooses when it wants to photosynthesize because it's based on things like, how dry is it out? I want to keep my stomates closed when it's dry. You know, I don't want to let my water vapor out. But when there's plenty of humidity, I'm going to open it and I'm going to photosynthesize. Now, what's interesting is that if we were to do that, we would, and this is being done, there are some adaptive buildings. Oh, and that the idea here, and I've said it before, is that the material is the system. For instance, the stomates are the system. There's no motors, there's no sensor, and then a motor, and then an actuator. The material of the stomate is the system. It is both the sensor and the actuator. It's really interesting. Same way with this Venus flytrap, you know? It literally grows in a way that it's pre-stressed into a certain curve, and then when it's triggered, the hairs are triggered by an insect, it releases that stress. So it's pre-stressed and it pops, kind of like those concave, convex tops of mint containers will do. So the material in this case is the system. Here's some adaptive frittings by Chuck Hoberman, who works with he's in the Harvard Graduate School of Design and works with biologists there. Now this is a fritting that in response to light opens and closes, becomes more translucent or more opaque. But it's done with motors right now. So really the Holy Grail is to take something like this, which is really cool in that it's adaptive, but that within the material itself, it's responding to the trigger that it needs, that is appropriate, whether it's light, acidity, electricity, whatever trigger is in the, or moisture. Whoop. There we go. Huh. There we go. Now, a big part of biomimicry is sensors. The military has been very interested for years in biomimicry. One of the reasons is the sensing capabilities of organisms far outstrip our own. These are compound eyes of dragonflies. There's a guy, and I had lunch with him today, Luke Lee. It's so great to meet these people when I come to university. Luke Lee is at the BioPoets Lab, and they actually created a lens that has multiple facets. Wow. I told the people who put this on me that I do tend to sort of make large movements sometimes. Multiple lens, compound eyes, a lens that has compound eyes, and is able then to be way better than a fisheye lens, for instance. So you can imagine in a building having these sorts of compound eyes, being able to see all around, because sensors will be important as part of this adaptive building. And you have that here. And actually, Luke Lee is now working with someone from the College of Environmental Design, an architect. You've also got an amazing resource here. You have a thing called CYBER, which is the Center for Interdisciplinary Bioinspiration, Education, and Research. More coolly said, cyber. And that's Bob Full and the robotics people and the people who are looking at how critters scramble and how they move over uneven surfaces and how they stick. This is, if you've never seen this, it's very cool. This is the gecko's foot, and these are the bristles on on the ends, the split ends at the end of this gecko's foot. These are the things that they mimic there. Also important in when we think about sustainability and we think about reducing the toxins that we use in glued together parts, and we think about what a mess it is, recycling-wise, to have things glued together to begin with. Imagine having gecko tape, strong, strong adhesion that is reversible, that you're able to send a product back at the end of its life, and you're able to peel it apart and reuse its parts. Those 5 simple polymers. Healthy, but without an arms race. Antibiotic resistance. You know, every single time you think about it, I know you do at Berkeley, every time you're using antibiotic, cleansers, sanitizers for your hands, you're realizing that there are bacteria somewhere hacking in immunity to that stuff going, they're the super bad bacteria. And it's things like MRSA, golden staph, multi-drug resistant bacteria. They're resistant not just to our antibiotics, they're getting resistant to our cleansers as well. And so the answer often is just use more antibiotics. And that's really biologically a very, they love that sort of a challenge. Organisms love that sort of a challenge. Is there a more subtle way to do this? This is a Galapagos shark. It's a loafing shark. It doesn't move very fast. It actually just sort of hangs out. It interested some scientists at the University of Florida because they thought, you can understand that a shark's skin, when water's moving quickly over it, would allow bacteria to be brushed away and allow biofoulant to be brushed away. But what about a shark that doesn't move quickly? Are they also free of bacteria? It turns out they are. They looked for chemical reasons for this? No chemicals. What's happening is structural. Turns out at a very, very small level, these diamond-shaped patterns, these denticles, they don't allow bacteria to get a foothold. So now there's a company called Sharklet Technologies that's making basically a thin film, sort of like a wallpaper that you can put on hospital tables, or doorknobs, or railings of staircases. And it keeps bacteria from settling. It repels bacteria, but without chemicals. And therefore, there's not the resistance. It doesn't breed for resistance. It doesn't encourage resistance. This is a lotus leaf, and this is probably the Velcro of our time. It's a self-cleaning leaf, as many leaves are, because of its nanostructure. And there are many, many products now. The thing about biomimicry, what's happening is that once scientists do the fundamental research and come up with a sort of a design principle that comes out of the leaf, it becomes what's called an effect. So you have the lotus effect, you have the peacock effect, sometimes people call it that for structural color. And those effects become platform ideas for lots and lots of technologies. So that's a lotus leaf right there, and those are the bumps. This is a ball of water. This is loose dirt that sort of teeters on those mountaintops, and this is a ball of water picking up that loose dirt and purling it away. That's the lotus effect. It's a self-cleaning structure. So the idea is not, how do we make a better detergent that has less phosphate in it? The idea is, how do we make our buildings able to be cleaned by rainwater with no detergent, with no sandblasting? Here's a paint. There's lots, look up lotus effect when you go home, you'll see lots of products. There's roofing tiles, there's building facade paint, there's a really nice fabric now that has lotus effect on it, and water cleans this rather than detergent. And rainwater cleans these buildings. This is Jill Banfield here at UC Berkeley. Their lab discovered a very interesting thing. And it's not yet being mimicked, but I think it's very interesting. In the time of nanotechnology, the thing that people are worried about, and rightly so, are loose nanoparticles. materials at a nano scale have different properties than they do at a larger scale. And do we know exactly what's going to happen as they interact with our cells? Not really. So you say, what in the natural world uses nanotechnology? And the answer is everything. Nature is nano. Nature starts with nano scale. And nature, I think, has an awful lot to teach us about how to do nanotechnology safely. How to embed, for instance, nanoparticles in a structure so that they don't abrade away. And here's an interesting one. There are bacteria, sulfur-reducing bacteria, that actually release to the environment nano-sized particles. They release those into the water. Now, lo and behold, they also release a protein that comes in afterwards and aggregates, remember the concentration, aggregates those nanoparticles together into a clump that fall out of the water column. I find that really interesting. I think there's something there. Manufacturing without fire. We basically, we got hooked on fire a while ago, and it is still the best thing since sliced bread. Now we have big fires, really, really high temperatures. I mean, to make something like that ceramic, right? That's what that bone is. That antler is actually bone. It's actually bone in this critter. Imagine the kiln we'd have to put that ceramic in, right? Of course, he doesn't do that. So the question is, how do you do low temperature ceramics? Or fibers. This is the fibers. This is the business end of a spider. It's a beautiful Dennis Kunkel electron microscope picture. Incredible. What we do is we manufacture at high heats, right? You couldn't do that if you were a spider. We do heat, beat, and treat. Nature does not use high heats or high pressures or toxic chemicals. It can't. It can't afford to. But it's got other ways of doing things. It's got ceramics, twice as tough as our high-tech ceramics, the inside of an abalone shell, which has been the model organism. And now, here in Berkeley, you have a team here that has come the closest I've seen to replicating the ceramic, the beautiful layered structure that is nacre. And they are creating a lightweight ceramic that is as tough as aluminum alloy, and yet very, very lightweight. Incredibly important for fuselages of planes, for cars, for building members. And that's right here. Here's Joanna Eisenberg again. Again, the manufacturing, self-assembling at room temperature. This is the best lenses known to the optics world. These are lenses that are on the outside of a brittle star. This is a glass-like substance, the skeleton of diatoms. All of these are being looked at. The process of making glass without fire is happening, and it's called self-assembly. And it's happening, University of Santa Barbara is the key place for this. Right here, there's a young man who won an award and is now looking at how do we replicate the glands of a spider. In other words, make a fiber manufacturing facility that works like the spinnerets. He's not actually going to be making it just like this, but he's going to learn the design principles to make a way of making fibers at low temperatures and squeezing them at very, very low pressures. Cooling without AC. This is a self-cooling organism. Researchers have found that above the black stripes, it's 10 degrees warmer than above the white stripes. There's fat under the black stripes, sweat glands under the white stripes. If you know your physics, that when you have something hot and the heat rises, it starts to create a thermal. And as it creates a thermal of heat rising off of these black stripes, there's a tiny convection current along the white stripes. elegant. People are laughing. It's elegant. Here's a self-ventilating structure. This is actually the design. My partner and I are building a new house, and it has a biomimetic element, which is this monitor here, which opens up, and you open up these windows, and the air comes out like this. It's very similar to what's happening here. You've got a mound that's higher on this Colombian ground squirrel mound. It's higher than this mound. Air going over creates a vacuum effect like this, and it creates a self-ventilating structure. Termite mounds. You've heard this story of the termite mounds are self-ventilating structures. There's the first building that was naturally ventilated using the termites' ideas. What's happening now is a really interesting project in which we're learning much more about the insides of a termite mound, layer by layer. It's a project called Termes. And then they're reconstructing the termite mound and doing computational fluid dynamics. What they hope is to be able to figure out what shape of tunnels to put in wall systems to create natural ventilation. What about at the city level? These have been mostly little, small, product-like ideas. But what's happening with biomimicry is that there's that ecosystem level as well. And working in city planning has been very, very interesting. One of the things that we're doing is, this is a project called Mannahatta, which looked at what New York City was like in the 1600s and of course, what it's like now. So it's an environmental history. I ask you, which of these systems actually gives back to the watershed of the Hudson Valley? And we know it's this one. You know, lots of cooling, lots of oxygen, lots of carbon storage, soils are being built, biodiversity is, and over here we sort of give it a pass. Oh, well, we live there. Well, the question is, what if we didn't give it a pass? What if we asked this system to do at least as well as this system, right? In terms of ecosystem services. We're calling it ecological performance standards. We're challenging cities to match the ecosystem services of the system that would be there if they weren't there, if we weren't there. Buildings, hardscapes, sidewalks, roads, all of them contributing to building soil, purifying air, purifying water, doing the things that we expect an ecosystem to do. I'm figuring we're at least as much of a complex adaptive system as a forest or a prairie. Can we match that? This is nature as measure. So we look at the unique ecological story of each place, and we're working in China. It's really fascinating. And we try to learn from the genius of the place. This is a place in India that gets 9 meters of rain. Big problem there is with soils. And so we begin to ask things like this. How many gallons in a storm are absorbed and then slowly released? And we meet that. What's the percentage of solar gain and reflectance of a natural system? And we try to meet that. What's the carbon sequestration? Number of tons per acre. What's the water filtration? The evapotranspiration. These are really aspirational goals. It's 20 years to get here, right? But without a goal, we're not going to ask much of ourselves. We're going to give ourselves a pass. So nature is setting the standard of this development in India. We go and we look at things like this. This is an ant, harvester ant. And when it gets monsoonal rains, the water slowly circles around that labyrinth. And even though its nest is made of soil, there is no erosion, creating roadways that have similar contours. Thinking about the fact that root systems on these very steep hills in soil erosive areas have something to teach us about foundations. And maybe our foundations have to be more than just vertical. Maybe they have to have a horizontal component. Maybe they need to do what these systems do, which is store water underground for the dry season. Roots literally on some of these trees will push water down and then redistribute it in a water bank. Imagine asking our cities to redistribute water in a water bank for the dry season. Imagine asking every single one of our roofs to have roof tips, drip tips, like rainforest leaves. Imagine having sediment collectors that learn from mangroves, which build millimeters of soil every year, lots. There are many cool, neat technologies in the natural world. And my life is about those, and finding them and being delighted by them, and then watching them actually be mimicked by brilliant designers and engineers and inventors. The most innovative design is more difficult to talk about, to point to get metrics around, and yet it is the most important one. And it is the fact that these emperor penguins, their genetic material, all they care about is their genetic material surviving. All survival means for them, all success means for them, is their genetic material 10,000 generations from now still being around. Not just in this generation, but 10,000 generations from now. And the only way they can do that is to take care of the place that's going to take care of their offspring 10,000 generations from now. And so they've developed a system that creates conditions conducive to life. Not just their own life, not just the life of their immediate offspring, but to life, to the system in general, to the system that keeps them alive, to those balls of fresh water and fresh air. Creating conditions conducive to life means building soil. It means purifying air, purifying water. It means figuring out as a species how to do that. It means figuring out how to be generous. It's so beyond meeting our own needs right now. I mean, our thinking, the regenerative design thinking, has moved to, are we a welcome species in our watershed? What are we doing with this big brain? For me, the things that you've seen tonight, I hope excited you. Yes, the technology's excited you, but I hope that part of that stone-like part of your heart might have melted a little bit. And you might have looked at these organisms and said, my God, they are not just beautiful. They are astounding, right? They have an intelligence. They have a wisdom about how to live here. A new way of viewing and valuing biodiversity, I think. That's one of the reasons that I'm in this work. One of the things that we're trying to do to avoid a gold rush, to avoid a second exploitation revolution, is to make sure that there's a Thanksgiving loop in every single one of these stories. We have an institute, Biomimicry Institute, a not-for-profit. One of the things we're doing is called Innovation for Conservation, where we're asking the companies that we work with and the companies that already have bio-inspired products to give back, to say thank you to the original patent holder, and to give a percentage of their proceeds to conserve the habitat of the organism that inspired them. So this is, one of the things that it's easy to do is to look at this and go, okay, well, there are scientists working on this, and they'll get back to us. But I would suggest that we're all designers, and that we've all got design problems we're looking at. And how do you consult nature? One of the biggest things is that we have this consulting firm, but my God, there's like 12 of us, you know? And there's a lot of biological information. How do we build the bridge? The flow structure, that biological information will flow into the design disciplines. One of the things that we're doing is we said to ourselves, what we need is just-in-time information. That's what Tom McCaig calls it. He teaches a class here called How Would Nature Do That, by the way. And he says that designers need just-in-time information. When they're designing, they need to be able to turn to a biologist and say, how would nature do this? And so we envisioned this and we said, you know, can we put this on the web somehow? So we started this thing called asknature.org. I really want you to check it out. We have this sort of Google-esque, you know, immodest goal, outrageous goal, of organizing all biological information by function. All biological information by function. So we're not doing it ourselves. It's a wiki, and we're collaborating with Encyclopedia of Life, and the scientists there are uploading things that they know that we might be able, functional adaptations. IDEO did the design. Check it out. It's kind of cool. I think you'll like it. It's meant to be a bio-inspiration site for you. And it's also like a social networking site so that you can meet the crazy people in this field. Come to our parties. You know, come to the biology parties. They're pretty good. I always get a question after this. And people say, what about us? All these organisms are so cool. But we are, you know, black sin, black mark on our soul, right? We are the condemned species. It is not in our nature to fit in here. We have bought that hook, line, and sinker, by the way. We have bought it hook, line, and sinker that we cannot love life and adapt our way to loving life. It's amazing. Look, we are a pretty cool species. You know, we really are. We really are. We are nature. It is a rhetorical paper bag I've been in all night, talking about learning from nature, learning. We are nature. We are nature. We are a very particular species. I reference this again. We are a very interesting species. But we are not aliens. We are of this place. We sprang from this place, and we are every bit the biological organism that wants our offspring and our offspring's offspring's offspring to live. Problem is, we're young. We're 200,000 years versus 3.8 billion years. That was when the first blue-greens bubbled up. 200,000. Now, people know these figures because of the stimulus, because you know what billion means now. 200,000 years is how long Homo sapiens sapiens have been here. 3.85 billion years, right? We are young. We're incredibly young. And we're toddlers with matches, let's face it. But can we mature? Why not? I think we can. I definitely think we can. I think one of the ways to maturity is to quiet human cleverness for a moment. To listen and then to emulate and then to give thanks. You know, but that quieting human cleverness, part of it is realizing that this nest and this building are similar in many, many ways in terms of intent. The organisms that made this building, this nest, the birds that made this nest, had one intent in mind. They always were asking themselves, how will the chicks fare here? That was their design program. It was life-centered. Life-centered. Period. End of story. Simple criteria, simple consequences. Severe consequences for not meeting the program. And I think that our artifacts are just like this. I really, really do. I think that our artifacts are natural. I think this building is natural. Is it well adapted? Natural selection will let us know that. Is it maladapted? That's the only question. And we are not aliens. And we don't have to jet off to some other planet. We belong here. This is our home. This is our home planet. We happened to inherit from that long line of rare species. We happen to inherit a lush and livable place. And our job is to learn to make of this place an Eden as well. And biomimicry is simply about realizing we don't have to do it alone, and they are here to help us. So I really would encourage you in the next 50 outrageous years to bring nature to your design table and to recognize yourself there. Good luck in what you do. Let's clap for the students who are going to be making our world. Good luck. Thank you. I went way over. I'm sorry.
If it's okay with Janine, will you take a few questions?
I will. Yeah, I definitely will.
Okay.
I definitely
If you have
will.
questions, please come forward to the mic quickly and ask questions. What? Students first. Thank you, Linda. Students first. Please come. Approach. And while they're approaching, just let me say, what a fantastic anniversary present you just gave us. Thank you.
Hi.
Hey.
So you talk about a lot of high-tech solutions, and I was wondering if maybe you could speak to some like low-tech biomimicry.
Low-tech biomimicry. You know, one of the things that people always comment on is, wow, that's like a 20-year research project to get materials that will do what you're talking about. But there are some things that we can learn from the natural world and just reassemble the existing products that we're already using. You know, putting your roof into a shape inspired by a rainforest leaf is not, you know, you don't need to wait for a new material to do that. And there are many, many, many bioclimatic solutions that are already in vernaculars, you know, that are already in culturally appropriate building vernaculars that I think might have been inspired by organisms. You know, I mean, I think we lose sort of the genesis of some of these things. You know, was the fishing web designed by a spider originally? You know, did it come from that? Were some of the earth homes inspired by organisms that make their homes with mud? I think that they probably were. So you know, it's interesting to look at the things that have lasted over generations and generations, the building forms that have lasted, and sort of ask who might have been the emulated in those.
Other questions? Come.
Hi, thank you very much for a brilliant lecture. I'm not a student at Berkeley. I'm actually a former student at Presidio School of Management, which is a MBA program, sustainable MBA, which you know, Hunter Lovings teaches
Hunter
that.
Lovins is right here.
Yeah.
Oh, she was right there. There she is, right there.
That's where I was pointing.
Yeah, I heard she corralled a few of her students to come here.
Yeah, almost all the left side is.
The left bank are Hunter students, good.
One of the things that one of my friends brought up, actually, when we were talking about the beetle from Namibia, when he was, you know, you mentioned that we can collect the fog on the top of the buildings, but she said, while this fog contributes to the to the climate in this. And if we're collecting the water out of the atmosphere and channeling it, what's going to be happening with the climate in this place? And I see a lot of the solutions that people make don't account for the climate, like putting the solar panels in the desert. How does it affect the larger picture?
Yep.
So do you see that biomimicry can account for the complexity of the systems and not just look at the one structure at a time?
Yes, yes, excellent question. It's using nature as model without using nature as measure can be dangerous, I think. Because when you use nature as measure, it talks to you about scale. It talks to you about sufficiency and excess. It talks to you about proper scale, right? That's using nature as measure. So, for instance, the idea of fog, I mean, fog is being captured by redwoods. A 100-foot redwood, I just read this, will, in a night, capture 4 inches of rain. 4 inches of rain. Now, we don't say, well, maybe redwoods shouldn't be capturing that rain, right? So we say, we are sitting in a place, we've got our buildings up. I really do think that the decisions need to include, and that's why this idea of ecological performance standards is important. How much water was collected by the system that was here before we were here? Because that gives you a sense of scale, of appropriate scale, so that we are not taking more than our share. And if we are taking more than our share, that we are replenishing way more than our share. I mean, that's a budgeting that I think we have to sit down as a species and begin to have. That sort of kitchen table conversation. What is our share? How much can we give back? You know? And again, while I certainly am not naive about what we have, the corners we have painted ourselves into. I mean, I got into this work out of my grief, so I know. But I also have got to believe that we can be a net positive benefit where we are. We're going to have an impact. We are going to have an impact. We are going to make a difference. You know that make a difference, you know those posters make a difference. We can't help but make a difference. It's the quality of the difference we make. You know, so for instance, if you look at a watershed and you look at beavers, beavers cut down trees and they create ponds, right, behind them. And you think, wow, that's not too good for the forest species, right? But that's only looking at one part of it. When you pull back up and you look at the whole watershed, you realize that beavers in a watershed are ecosystem engineers, just like we are, ecosystem engineers. But studies have shown that at a watershed level, they actually increase diversity as a result of being there. Their ponds are not permanent. Their ponds break, the dams break through, and those former forests become meadows and become berry bushes and then become forests again. And they move on to another patch. And they do the same thing. And there's a patch, there's gaps of openings, right? And over the long run, in that watershed, it's better off than being there. That's a positive difference of an ecosystem engineer. Can we actually give ourselves that assignment? Right? And it's going to take asking a question, just like you did, every single time we do something. But I would also say to you, don't assume that everything we touch turns to soot. Because if we do, we relinquish responsibility and we say, oh, well, it's just not in our nature. You know what I mean? I'm kind of holding us to a different standard.
Thank you.
Hi. I was wondering if you could give us an example in nature that involves a closed loop cycle involving zero net energy or zero net waste that we could possibly emulate.
Oh my. Let's go hiking tomorrow. One of the really interesting things that you could do sometime is go into a forest and look at the water that's in the stream in that forest, and how the materials, it comes through the forest floor and it gets filled, right? It's going through all these nutrients, right? And yet, that water it's not leaking. That system is not leaking a whole lot of precious nutrients. It's not leaking them out, It's really, systems, they're open to energy, and they're open a bit to materials, and this is most systems you look at. Look at a forest, look at a prairie, look at a coral reef. These are systems that make the most of what they have. You think about a forest that's on the same piece of ground for 400 years until a forest fire comes along. The only materials coming in are some minerals in rainwater, some nutrients in rainwater perhaps, and some migrants that come in. The rest of it is all of the soil, right? And of course, a lot of energy comes in, a lot of water comes in. But the materials are recycled over and over, reused, upcycled, I would say, upcycled into new, into plant bodies and into a bird body and into a beetle body, right? But those materials, that's your model of a food web ecosystem. And it's, look at a system that stays on the landscape for a while. That would be your model.
Okay, thank you.
I actually have to apologize to those who are in line. Janine has not eaten dinner yet, and we've already kept her longer.
I kept her longer.
We're going to say one more with apologies, but I really do feel responsible for feeding her. So go ahead.
I was already nervous. Now there's more pressure. Hi, I'm a fellow Montanan, actually. I live in Missoula, so you made me homesick.
From where?
Missoula.
Oh, nice.
Anyway.
That's the bitter root.
I recognize.
Yeah.
So I design work for people and help organizations, businesses design their organizations. And I know in your book you speak to building your business like a mature ecosystem. But so I guess I just wonder, when we look at this notion of the big picture with the penguins, of we're here, they're here to save themselves. Would you say that biomimicry might say that, like, the work that we are here to do is just that? I mean, if you're designing someone's career or helping an organization speak to that, how does someone like me help an institution or an individual integrate biomimicry if they're not a designer, say, in any role? I guess, beyond, I work with a lot of designers, but I work with a lot of other types too.
So you're asking, can biomimicry help in, say, organizational development, or the way we organize our teams, or the way we do our work? And I would, and when you talk about biomimicry and social applications, I would make a caveat that you have to really be careful about where you look for your models. Because we're not, we're not baboons, and we're not bees, and we're not lions, and you know what I mean? So if you look at a particular species, you will not find the right level of analog. And actually, I think it can be harmful to look to the natural world for your social mores. Social Darwinism comes to mind. Okay, so with that caveat, is there a place where communities, companies, communities, can learn from communities in the natural world? Yeah, if you do it at a level of, you're a complex, adaptive ecosystem. You know, the internet is, a city is, a community is, a company is. And an ecosystem like a forest is the same sort of a complex adaptive ecosystem. There's a field called community ecology, which talks about all the players in an ecosystem and the roles they have with one another. And there's wonderful new research about, and ongoing research about cooperation, coevolution, mutualisms in the natural world that I think are very, very relevant. So community ecology is one of the places I would steer you. The other place is a field called resilience science, which is the study of why some ecosystems can survive a hurricane or a big disturbance and can build back and keep their integrity, remain a coral reef or remain a forest, while other systems get hit by a storm and then they just never come back. The question that scientists have said is, what are the characteristics of each? And those principles, those design principles of the resilient system, I think are really important. So it's a long answer, but it is pretty important because a lot of people will go instantly to science light on the social stuff, you know. But I think that there are really good, really science-based pearls out there. So get with an ecologist.
Okay.
They'll be happy to bore you with this stuff. You're welcome.